was the most interesting applied robotics problem, period. It was a place where you could make products that were essentially immediately useful. We don't have 100% reliable autonomy. You need supervision for it to be useful, but people buy our products because it adds value to their lives. This is actually quite unique in robotics. There are not many use cases where this is the case. You can have some kind of hyper-specific industrial robots are obviously useful. Robot vacuum cleaners. I'm a big fan of robot vacuum cleaners. There's robot lawnmowers, and that's roughly it. There's not that many places where you can do like applied AI, applied robotics in the real world. And that's why I thought self-driving was so cool. And then the other thing is I just really like the open source nature that we have with OpenPilot and that we're trying to promote. I think an open source future is just generally better for everyone.
Well, yeah, I'm particularly interested in this conversation because, a lot of times on the show, we have really interesting people on, but sometimes they're and great discussions, but sometimes they're constrained in terms of what level of detail they're able to talk about kind of architecture and things like that naturally, because they're maybe working on certain proprietary things. And with having so much in the open source world, with Comma and OpenPilot, I'm kind of interested if maybe from a high level perspective for those out there that are listening that might not have an idea of like what sort of architecture and kind of main components are part of a self-driving or autonomous system. Like OpenPilot is maybe a piece of that and fulfills a role. You have the devices. Could you just give us like a mental model for how to think about how these pieces fit together, what's where, and what components are needed to make, the system
Sure.
work, I guess?
So we're talking about ours in particular, right? Or just in general?
Yeah.
Sure. Yeah. So ours in particular, we have a device that you can install in the car. The device has compute and it has some cameras and then some other sensors like GPS and IMU that are not necessarily that needed, but they're in there. That device then runs some machine learning models by looking at the road that tells you where roughly to drive. And concretely, that is a longitudinal acceleration and a curvature of the road. So that's like an angle of the steering wheel. I'll talk about how that works internally later, but in runtime, this is really all that happens is there is just a machine learning model that takes in the video input and outputs those actions of acceleration and curvature. And then that goes to some API that, we kind of develop that interfaces with all these different car models. So we reverse engineer the canvas of the car. And so we can understand what messages we need to send to command, steering, gas and brake, and do all the auxiliary stuff of like the engagement state, all those kind of things that are needed to do autonomy in a car. So that's basically what's happening at runtime. We just have a device, it runs some models, it outputs the actions to take, and then there's a car API layer that, is reverse engineered for every type of car we support that sends messages on the CAN bus to do the certain actions. Then those models themselves that we train, so we've been kind of talking about end-to-end training for a long time. So they're end-to-end in the sense that they take in video and they output actions. There's no intermediate space of, our cones detected, traffic lights detected. That all doesn't exist. And very high level, our training stack looks like we have hundreds of millions of miles of humans driving. We sample some of that. We teach the model, okay, if a human's in this situation, this is the most likely trajectory they're going to take. If you train that directly, you get a system that doesn't really work. This is like a well-known machine learning problem that's not necessarily well understood, but you can't just do imitation learning and expect things to work in the real world. You need to expose the model during training to mistakes and show it how to recover from those mistakes. And we do that by training in a simulator where we can introduce, going off the center of the lane line, and then we can supervise, okay, this is how you would recover from this. That's very high level how things are trained and how things work. I don't know if there's anything I missed there or any questions we can discuss there.